Right, welcome back. We finished now with the section dealing with the machine which we call the electrical motor. So we're now going to the second section, which is the generator. So if you can focus here on our PowerPoint, you will see I've got the generator. I'm going to look at the very same things that I've looked at previously: components, the principle, energy conversion, uses, and the explanation of how it works. And a lot of this, guys, are just the opposite of what we've seen now in the electrical motor. A lot of it is working on the very same basics. All right, let's look at the energy conversion. We have mechanical energy, which is now converted to electrical energy. Something you're going to get it for 2 marks. Make sure that you know and understand why this is the energy conversion. All right. Okay, what is happening there actually is that I am now turning electrical conductor in a magnetic field. So whenever we do that, then we know there's a change in the flux, and potential difference will be induced, and a current will be induced in that conductor. So it works on the principle, in other words, of induction. I am providing the motion, the movement, by a force on the armature which is turning it, and electricity, current, is now the product. So that's why that is my energy conversion. Mechanical energy converted to electrical energy. All right. So if we go to the next part, the movement supplied, electricity the product. What do we call this principle then? Or how can we predict what will be happening? The rule we're going to use there is Fleming's right-hand dynamo rule. Fleming's right-hand dynamo rule. That rule goes with induction. So immediately you can see in the electrical motor we use the left hand. In the generator we are going to use our right hand. So that is just something which is the opposite. So if you look at this drawing of a simplified generator, again you will see first change, there is no external electricity supplied through the external circuit. All right, so in this case we have the same components. There's my magnet, there's my armature with the windings that's going to be turned by me manually. There is my brushes, and in this case I've just shown an example. There's another possibility instead of split rings, and this is what we call slip rings. It's not splitted, it's a continuous ring, just like the ring that I've shown earlier, but there's 2 of them now. And the one side of my armature is touching the one, and the other side is touching the other one. And that actually completes my circuit. Now I can work out in which direction will this generator, do I need to spin it if I want to create a current, induce a current in that direction through the armature. So for this now I will use my right hand rule. So if you can focus for a moment here on my right hand, then you will see that the very same fingers, 90 degrees between each other, the direction of force, magnetic field direction, current direction. All right, so which 2 did I provide here? I provided you with the magnetic field direction, which is from north to south, so it will be from the left to the right. I've provided you with the induced current. So I want to know in what direction am I turning this generator thus. So if I apply my right hand rule, and please guys, take your right hand, I can now go and say, all right, my current direction will be in that direction. It is going from north to south, the index finger. So it means now that my thumb at that section is showing in that direction, upwards. All right? So if that part is going up, it means that that part will be going down. So up and down gives me a clockwise rotation. So I have to manually rotate this generator clockwise. And the generator is generating electricity because of the principle of induction. And I'm using Fleming's right-hand dynamo rule to be able to explain this principle. All right, so that is our generator. Just another example that I showed you. Remember, around any electrical conductor where electricity is conducted, there is a magnetic field. I've shown you how to indicate it on paper. But when there is no electrical current in this conductor, and I place it in a magnetic field, I just have to change the flux. So I just have to move this conductor. In that case, then, an electrical current will be induced. And that is what we looked at now. All right. There I've shown you just a picture of the electric motor, which we've gone through. So clearly you can see there's my power supply. You can immediately see also the split ring commutator, which is a very important section, which we dealt with. There I've shown you electrical motor, whereby I can just check in which direction will it experience a force, but I want to just go to the generator. So you can clearly see the changes. Current is produced. I am manually, mechanically turning this thing around. The electricity that is now induced, I can use that to work for me. In this case, it can brighten up a bulb. I can use it to have light. So where can we use generators? We are using generators every day for the supply of electricity in our homes. So a very easy application of where we are using it. You will read in the newspapers these days, we are using generators in wind applications, where with wind we are turning them. And that turning of the armature in a magnetic field is inducing electricity, and that electricity is being used in our homes. We can do it by water, hydroelectrical, where at some of our rivers we have hydroelectrical schemes, which also provides electricity, where water is used to turn the armature. And when the water turns the armature magnetic field, electrical current is induced. Yes, there's lots of applications these days by which we turn the armature mechanically, mechanical energy converted to electrical energy. All right. Okay. Before I go on to the part of alternating current then, let us just go back now to the example of the generator.